Absolute and conditional convergence. Before jumping right into it, let's lay some foundation. Given any series, the sum of a sub n, we can consider the corresponding series the sum of the absolute value of a sub n, which is the absolute value of a sub 1 plus the absolute value of a sub 2 plus the absolute value of a sub 3, and so on. Notice the terms are the absolute values of the terms of the original series. So basically, we're taking each term and making it positive. That brings us to the absolute convergence test, or I think about it as the absolute value convergence test. If the sum of the absolute value of a sub n converges, then the sum of just a sub n converges. And if we take a moment to think about that, what we're doing is we're giving ourselves a challenge. We are making all of the terms positive, and if that converges, well, then the series that potentially had some negative values is also going to converge because it's smaller. If it had some negative values, then it's going to be smaller than the one that has the positive values. So I like to think about this as a challenge to ourselves. We're making all the terms positive, which is making it potentially bigger, and seeing if that converges. Well, then, of course, the one with negatives is also going to converge. Let's try to understand this with an example. Use the absolute value convergence test to determine if the sum of n equals 0 to infinity of negative 1 to the n times 1 over 2 to the n converges or diverges. So what I'm going to do is I'm going to rewrite this for a second. It's the sum of n equals 0 to infinity of negative 1 to the n over 2 to the n. And so it has negative terms. If I start by substituting in 0, my first term is going to be 1, and then the next term will be negative 1/2, and then positive 1/4, and then negative 1/8, and so on. This is actually geometric, so this isn't the most efficient test to determine convergence or divergence, but it's going to help us understand this idea. So we have this alternating series. We can visualize it here. We have 1, negative 1/2, 1/4, negative 1/8. So these terms will alternate. Now, what we're going to do is we're actually going to make our lives harder here. We are going to make all of the terms positive. So we are going to consider the sum of n equals 0 to infinity of just 1 over 2 to the n. So now this is still geometric. This is the sum of n equals 0 to infinity of 1/2 to the n, but this has all positive terms. So any value that was below the x-axis will reflect up and be above the x-axis. And now we want to see what happens when we add up all of these values. Well, again, this is geometric with r is equal to 1/2, and the absolute value of r is less than 1. So again, this was geometric, and so this converges. Well, we basically made it bigger and it converges, so that means that the original series that had alternating terms, right, that had adding and subtracting, that's also going to converge. So we can say by the absolute value convergence test, the original sum, negative 1 to the n over 2 to the n, converges. Now, I just want to remind you, this was not the most efficient test. We could have just applied the geometric series test on the original series, and we could actually find the sum of the series, thinking about this as geometric, but this is just to illustrate the idea of the absolute value convergence test. Now we want to determine, does the sum of n equals 1 to infinity of sine n over n squared converge or diverge? So here, if we start to think about the tests that we have for convergence or divergence, the test for divergence is not helpful. This is not geometric. It's not a telescoping series. We wouldn't really think to do the ratio or root test. And right now, it's not a candidate for any of the positive term tests because sine n alternates between positive and negative values. So this is going to be a great candidate for the absolute value convergence test. So we're going to start by considering the sum of n equals 1 to infinity of the absolute value of sine n over n squared. Well, n squared is always positive if I substitute in 1 or greater. So we're going to have the sum of n equals 1 to infinity of just the absolute value of sine n, and then we can just leave n squared alone on the bottom. So now we have a series with all positive terms, so we can use some of our positive term tests. And the one I'm going to focus on is the comparison test, specifically the direct comparison test, because what I want to do is just take a second to note that the absolute value of sine n is less than or equal to 1, because the sine function in general is alternating between -1 and 1. So when we put absolute value bars around it, it's definitely less than 1. And we want to go ahead and think about when sine n in absolute value bars is divided by n squared. So if we divide both sides by n squared, the inequality will still hold because we're dividing by a positive value. All right, well, 1 over n squared is a p series. So if I think about the sum of 1 over n squared, p is equal to 2, which is greater than 1. So this is a convergent p series. And notice that it's bigger than our absolute value of sine n over n squared. So if we have a bigger converging series, that is helpful in terms of the direct comparison test. So we can say by the direct comparison test, the sum of n equals 1 to infinity of the absolute value of sine n over n squared converges. Finally, we can conclude that our original series converges by the absolute value convergence test. So we write by the absolute value convergence test, our original series also converges. Now we're going to define what it means for a series to be absolutely convergent. If the sum of the absolute value of a sub n converges, then we say that the sum of just a sub n converges absolutely or is absolutely convergent. So in the last two examples, we found that the sum of n equals 0 to infinity of -1 to the n times 1 over 2 to the n converges, and the sum of n equals 1 to infinity of sine n over n squared converges. But we did that by checking the sum of the absolute value of a sub n. So because we found that they converge by looking at the sum of the absolute value of a sub n converging, we could also say each converges absolutely. So we could say the original series that has the negatives converges absolutely because we checked what happens when you make all the terms positive and those converged. So again, it's like we challenge ourselves with the harder positive term series, and that converged. So we say the original series converges absolutely. Let's look at an example. Does the sum of n equals 1 to infinity of -1 raised to the n minus 1 over n to the 1/2 converge absolutely? So what we have to do, again, is challenge ourselves and look at the sum of n equals 1 to infinity of the absolute value of the general term. Well, what that's going to do is have us ignore that numerator that makes terms alternate. Our terms are not going to alternate. They're all going to be positive. So we're considering the sum of n equals 1 to infinity of just 1 over n to the 1/2. So looking at this series, this is a p series with p equal to 1/2, which is less than 1. So this is a divergent p series. So what that means is that the answer to this question, does this original sum converge absolutely? No, it doesn't. When we took out the negative terms, the series got too big and it turns out that it diverged. So this series does not converge absolutely. That last example brings us to the idea of what it means for a series to be conditionally convergent. If the sum of the absolute value of a sub n diverges, but the sum of a sub n, the one with the negative terms, converges, then we say that the sum of a sub n converges conditionally or is conditionally convergent. So far, in that last example, we found that the sum of n equals 1 to infinity of -1 raised to the n minus 1 over n to the 1/2 does not converge absolutely because the sum of the absolute value of a sub n diverges. But we can still check whether the original series converges, the original one that has those negative terms. All right, so we are now being asked, does the sum from n equals 1 to infinity of -1 to the n minus 1 over n to the 1/2 converge conditionally? So in order to converge conditionally, we need that the sum of the absolute value diverges. Now, we already showed that, so I'm just going to recap it here. We know the sum of n equals 1 to infinity of 1 over n to the 1/2. So we made that general term positive. This was a p series with p equals 1/2, which is less than 1. So this was a divergent p series. So that tells us that this series does not converge absolutely. And to converge conditionally, that would mean that the original series with the negatives converges. Well, notice that we have this alternating piece here. So to check whether this original series converges, we're going to use the alternating series test. So now we're going to again check n equals 1 to infinity of -1 raised to the n minus 1 over n to the 1/2. Keeping in mind, again, it's alternating, so let's go ahead and focus on b sub n, 1 over n to the 1/2, the piece without the alternating factor. And we want to check those three conditions about b sub n for the alternating series test. So b sub n, is this positive? Yes, it is. B sub n is positive when we substitute in values 1 or greater. And then is b sub n plus 1 less than b sub n? Yes, so if we substitute in n plus 1, so we have n plus 1 to the 1/2, is that less than 1 over n to the 1/2? Yes, because bigger denominator, smaller fraction. So yes, and then the limit as n approaches infinity of 1 over n to the 1/2, does that equal 0? Yes, it does. So we can go ahead and conclude by the alternating series test, the sum of n equals 1 to infinity of -1 to the n minus 1 over n to the 1/2 converges. So it converges conditionally. Yes, it converges conditionally because when we made all the terms positive, it diverged, but when we kept those negative pieces in, it still converged. Before moving on, here's a helpful way to think about this. The series, the sum of n equals 1 to infinity of -1 raised to the n minus 1 over n to the 1/2 only converges with the condition that we keep the negative value terms in the sum. That's why we call this converge conditionally or conditionally convergent. The series only converges on the condition that we keep the negatives. But if we make everything positive, then it doesn't converge. Now, finally, we've reached the wording of a problem that you would get on a quiz or exam. Does the sum of n equals 1 to infinity of -1 to the n minus 1 over n cubed converge absolutely, converge conditionally, or diverge? So those are our three possibilities here. Now, we're going to go ahead and check first if it converges absolutely. So we're going to go ahead and consider this series with positive terms only. So we're going to consider the sum of n equals 1 to infinity of the absolute value. And that, of course, is going to affect the numerator, that alternating factor, and it's going to have us look at the sum of n equals 1 to infinity of 1 over n cubed. So this is a p series with p equal to 3, which is greater than 1. So this is a convergent p series. So what we did was we looked at the absolute value, we made it bigger, we challenged ourselves and made the series bigger, and it turned out that that series converged. So we say that the original series converges as well, but we get to say that it converges absolutely. So we can say, therefore, the original series, n equals 1 to infinity of negative 1 to the n minus 1 over n cubed converges absolutely. And we're done. We don't have to check or apply the alternating series test because when we check the positive term series, if that converges, then the original series converges, and then we get to say this stronger piece of information that the original series converges absolutely. This example here is kind of generalizing some of what we've done previously. It's asking for what values of p greater than 0 does the sum of negative 1 raised to the n minus 1 over n to the p, A, converge conditionally, and B, converge absolutely. So again, we're trying to figure out what values of p would we substitute in right here to make this series converge conditionally, and what values would we substitute in to make this series converge absolutely. We'll start by thinking about this series converging absolutely. So what we would do is we would consider the sum of the absolute value of negative 1 to the n minus 1 over n to the p. Well, what that does is it removes that alternating factor, so we would just be looking at 1 over n to the p. And this is just plainly a p-series. So when would this p-series converge? Well, it's going to converge when p is greater than 1. So that means that when you substitute any value of p greater than 1 in here, this sum will converge. And that means that the original series will converge absolutely because we made the general term positive, and whatever makes that converge, those values will make the original series converge absolutely. So the set of values is values p greater than 1. And we actually did a specific example of this. We looked at the sum of n equals 1 to infinity of negative 1 to the n minus 1 over n cubed in a previous example, and we found that this converges absolutely. And what is that p-value there? That p-value is 3, which is greater than 1. So now what values of p are going to make this series converge conditionally? Well, it's basically everything else. So our p-values have to be greater than 0, but not greater than 1. So what that's going to do is it's going to leave us with p-values that are greater than 0, but less than or equal to 1. So this is the interval that answers part A. And so let's take a moment to sort of think about this and think about the previous example that we did that can help us understand why this is true. We looked at the sum of negative 1 to the n minus 1 over n to the 1/2. And when we considered the absolute value, when we considered 1 over just n to the 1/2, since p was equal to 1/2, which is less than 1, this was a divergent p-series. But when you keep in the alternating piece, we were able to show by the alternating series test, we showed the 3 conditions, this converges. So this example where p is 1/2, which notice is between 0 and 1, including 1, so it's in that interval, we found that this was conditionally convergent. So here's an example that helps us understand why that set of values for p would create the original series to be conditionally convergent. So any value between 0 and 1, including 1, because if we have exactly 1, what's going to happen is we're going to get 1 over n to the first, which is the harmonic series, which we know definitely diverges. But if we keep in that alternating factor, the alternating harmonic series still converges. So all these values of p will make this converge conditionally, and any values of p greater than 1 will make this series converge absolutely. For this example, we want to know, does the sum of n equals 1 to infinity of negative 100 raised to the n over n factorial converge absolutely, converge conditionally, or diverge? When we see factorial, we tend to think about applying the ratio test. We have a little bit of good news there. It turns out if a series converges by the ratio test, root test, or is a convergent geometric series, It converges absolutely since these apply the absolute value. So we get converges absolutely from all three of these tests because these already take into account the absolute value of the general term. So let's apply the ratio test here. We're going to go ahead and find the limit as n approaches infinity of the absolute value of negative 100 to the n plus 1 over n plus 1 factorial. And then we would divide by a sub n. So this is the a sub n plus first term. And instead of dividing by a sub n, we'll multiply by the reciprocal, n factorial over negative 100 to the n. And then we'll go ahead and attempt to simplify this. So these absolute value bars here are going to allow us to ignore the negatives. So what we're going to do is we're going to say the limit as n approaches infinity. And then we're going to have 100 to the n times 100 to the 1. So this negative 1 to the n plus 1, I'm ignoring because of the absolute value bars. And then n plus 1 factorial, I'm going to write that as n plus 1 times n factorial. So I'm going to kind of leave out that n plus 1 piece, and then what's left is n factorial because it's going to cancel in a second with the n factorial up here. And then we have just 100 to the n. So again, those absolute value bars got rid of this negative 1 to the n factor. And so we can do a lot of simplifying, which is nice. The 100 to the n's cancel, the n factorials cancel. And what I have is 100 over n plus 1. So as n is approaching infinity, the denominator is growing bigger faster than this constant on top. So this limit is equal to 0, which is less than 1. And so we can apply the ratio test. By the ratio test, the series converges. But what we get to say is it converges absolutely. We don't have to do any additional anything. By applying the ratio test and taking the absolute value of that ratio, we automatically get converges absolutely if we get a value less than 1. Before looking at our next example, I want to give you a set of steps for determining absolute convergence versus conditional convergence, or divergence. First, if possible, we want to use the ratio test, root test, or identify if the given series is geometric, because those are going to give absolute convergence or just divergence. If these tests cannot be applied, take the absolute value of the series and use an appropriate test on the positive term series, like direct comparison, limit comparison, integral, or p-series, to determine if it converges. If the positive term series converges, you are done. The original series, we can conclude, converges absolutely. If the positive term series does not converge, now you must check whether the original series with negative terms, with an alternating factor, converges or diverges. So if it converges by the alternating series test, then the original series converges conditionally. Otherwise, the original series diverges. Here we're being asked, does the sum of n equals 2 to infinity of negative 1 raised to the n plus 1 times 1 over n times natural log n converge absolutely, converge conditionally, or diverge? Now, based on what we just learned, it'd be really nice if we could use a ratio or root test, but unfortunately, those are not going to work. So we have to just move forward and check whether or not the sum of the absolute value of the general term converges or diverges. So we're going to go ahead and consider the sum of n equals 2 to infinity of the absolute value of negative 1 to the n plus 1 over n times natural log n. We can rewrite that as the sum of n equals 2 to infinity of 1 over n times natural log n. And the starting index is 2 because if we start with 1, natural log of 1 is 0, and that would make the first term undefined. So that's why we're starting with 2. And the test that we're going to use on this series is the integral test. So if I take a moment and think about the function f of x equals 1 over x natural log x, for values greater than 2, this is a positive, continuous, and decreasing function. It's decreasing because if I substitute in x plus 1, the next term, 1 over x plus 1 natural log of x plus 1 would definitely be less than 1 over x natural log x. So bigger denominator, smaller fraction. So we meet the conditions to apply the integral test. And so we'll find the improper integral from 2 to infinity of dx over x ln x. And this is a pretty straightforward u substitution. We'll let u be ln x. Du is 1 over x dx, which is perfect because that's exactly what I have here. And let's see, we'll set up our limit first. So the limit as n approaches infinity of, actually, I don't want to use n. We already have n's going on. Let's say t approaches infinity of 2 to the t, and then dx over x ln x. Now I'll apply my substitution. The limit as t approaches infinity of my limits of integration, if I substitute in 2 into ln x, it's going to be ln 2. And then up here, if I substitute in t, we're going to have ln t. And then we'll have just du over u. And so we have the limit as t approaches infinity, natural log absolute value of u, evaluated from ln2 to ln t. So we have the limit as t approaches infinity of natural log of t minus natural log of 2. That's kind of fun. And what's going on there is if t is approaching infinity, natural log is approaching infinity, natural log of infinity is heading towards infinity. This is just a number, so we're going to have infinity minus the number. So this is infinity. What does that mean? That means the improper integral diverges. So since the improper integral diverges, so here, diverges. So by the integral test, the sum of 1 over n natural log n diverges as well. So what do we know so far? That our original series does not converge absolutely. It would need to have converged here with just positive terms only to have converged absolutely. So now we're going to go ahead and check if it converges conditionally, if it converges on the condition that I keep the alternating part. So I'm going to go ahead and kind of put a little barrier here. And so we're going to go ahead and consider the sum of n equals 2 to infinity of negative 1 to the n plus 1 over n natural log n. So this is alternating. So let's go ahead and peel off that b sub n part, 1 over n natural log n, the part that doesn't have the alternating factor in it. And let's recognize that this b sub n is greater than 0. B sub n is decreasing because, again, 1 over n plus 1 natural log of n plus 1 is less than 1 over n natural log n. And then the limit as n approaches infinity of 1 over n natural log n is 0. So I have a constant over a big number, right? That's going to 0. So all three of these are satisfied. So when the alternating piece stays, then we have, by the alternating series test, this sum does converges. So it converges conditionally. So it conditionally converges. Now, the other possibility was that it could just completely diverge. So we could have taken the absolute value, checked that, it diverged. We could have kept the alternating piece in and checked that, and it could have not worked. And so we could have found that this was divergent completely. It doesn't matter if we keep the negatives or not. So we still have those three different possibilities. So we check the positive version first. If the positive version converges, then we're done. We don't have to do anything else. But because the positive version diverges, then we have to check the version that has the alternating piece. Let's wrap up by summarizing the main ideas. Given an infinite series with some negative terms, the sum of a sub n, if the sum of the absolute value of a sub n converges, then the sum of a sub n converges absolutely. But if the sum of the absolute value of a sub n diverges, and the sum of a sub n still converges, then the sum of a sub n converges conditionally. Now, some important notes. Note 1, if a series converges by the ratio test, root test, or is a convergent geometric series, it converges absolutely. And the second important thing is if you're given a series with only positive terms, then when it converges, it always converges absolutely. So it's not really a question that you will see because it's already all positive terms. So we are usually given an infinite series with some negative terms and asked whether it converges absolutely, converges conditionally, or diverges.